You've actually already done areas between curves before, because when you've done areas under curves, you've looked at a curve like this, and you've gone from, let's say, x equals a to x equals b. You've looked at this region right here. And you're actually between two curves. What curves are you between?
That one
Exactly. F of x and y equals 0. So when you've done this integral, you've been writing the integral from a to b of f of x dx using the fundamental theorem of calculus part 2 and getting a definite integral. One way you could expand this and not change anything, you've actually been doing this. The integral from a to b of, can someone get the door? F of x minus 0 dx. You've been subtracting nothing from it. You don't normally write that in because you don't need to, but you've subtracted nothing from it. So what changes if I were to say, you have, let's say, oh, that's a poor graph. Let's make it better than that. Y equals x squared, and let's say y equals negative x plus 2, let's say x minus 2. Yeah, I gotta move it to the right. Yeah, it's being cranky, right? X minus 2 squared plus, I don't know, 3. I'm just adding something there. If I asked you for the area enclosed by those two curves, you're doing something similar. Let's say this one was, excuse me, this one is already labeled, I guess, so we can just use it. Which one is our upper function and which one is our lower function for the boundary? The green one is the upper and the blue one is the lower. So which one do you subtract from which? You subtract the blue from the green, exactly. So what are you going to end up with? You're going to end up with an integral of the upper function, which is negative x minus 2 squared plus 3. And what are you going to subtract from it? X squared, and this is all dx. Now that, as it's written right there, is that a definite or an indefinite integral? That is an indefinite. So if we wanted to find this definite integral, what would we need to find? Point. We need to find the intersection points, exactly. So you'd plot the intersection points. Sometimes these are set up nicely, sometimes they're not. But this is a quadratic, so let's just say that's x equals a, and this is x equals b. So you're going from a to b. So the math has not changed. The integration methods will still apply. You'll still use u substitution on some of these, trig substitution, you'll simplify, you'll still do battle with integrals, but now you're adding another layer to the setup. That is the area enclosed by those two curves. You have to be careful and then ask yourself which one is the upper bound and which one is the lower bound. That's it. There's no other. What do we think? Do people agree with the first one? Who agrees? The only thing I'll say is that I really don't like mixed fractions, so please write this as e minus 3 over 2. I really would prefer that. It's the correct answer, and I'm not going to take it off, but it's really nice. I mean, Griffin can kind of get away with it because his handwriting is really neat, but when you start using mixed fractions and your handwriting is not good, it makes my life horrible, okay? Because in grown-up math land, what does this mean? 2 times a half. 2 times a half. Don't use mixed fractions if you can help it. Okay, so Griffin, you said you found your error on this one?
Yeah.
What is it?
It's 2x minus x squared. I'd mix up the lower number.
You mixed up the lower number of integration?
It's not x.
Oh, so it should be this?
Yeah.
Yeah, so if you did this on the AP test and you realized that it was just flipped, as long as you make a note and say exactly what you're doing, you could say like, this needs to be flipped, like write a sentence out. You're totally fine just going, okay, the answer should be 1/3. But if you don't, if it's a question where you need to show your work and you don't say what the problem was, you can't just say negative 1/3, answer's 1/3. Yay! Multiple choice, it doesn't matter. That's fine. But on this, you'd have to explain it. Does that make sense? So, here we go. So the kids, how does this one look? How does this picture look? It's pretty good. So he looked at this area. You can't really see the shading, but do you see what he shaded right here? So how many of you spent the time and graphed the functions? Okay, so you should have something that looks like this. You have one function that goes down like this and one function that comes up here, but it gets cut off right there. So what region is he finding the area of? This and this. So what's the one challenge to this definite integral?
Switches upper bound.
Upper bound and lower bound. The upper bound starts off one and then it changes to another. It changes, right? So you have to do 2. So The challenge here, though, Colin, is that should you end up with 0 on this? Does the area exist on this thing? It does exist. So theoretically, you should not get 0. So there's some algebra mistake here which we can try to find. But your setup is great. You recognize that you had to switch, and you broke it appropriately. Where do these two functions intersect? Where does sine equal cosine? Pi over 4. Pi over 4. So you know it's going to go from 0 to pi over 4 and pi over 4 to pi over 2. And it's absolutely correct. The one thing you can check, which one's above here? Oh, this is the cosine. So you have cosine minus sine minus cosine. My guess is that there's an errant negative sign somewhere in there. That is absolutely a really, really common thing. You did something I like, which is you isolated y in the first function, which is good. If you do that, you know, what's the original function? Y squared equals what? 2x plus 6. So y is equal to plus or minus the square root of 2x plus 6. So you isolate it, and I like what you did. You took the upper function and subtracted from it the lower function. But what's the challenge with that? Is this a function? No, it's not. That's why it's plus or minus. Plus or minus is not a function. So if you graph this accurately, you have to be very, very careful because this function turns back on itself. Do you understand what I'm saying? So let's see what this looks like. Those are your two functions right there. Yeah. Here's the region that you found the area of. So is your area bigger or smaller than what you need? Smaller. It's smaller because what does the function do after it gets to its like sideways vertex right there? It doesn't. It terminates. But what is the relation y squared equals 2x plus 6? It goes back, right? So there's too much. You counted too much. You went too far over, and you ended up, this extra bit gets added in on yours. Do you want that in there? No, you have to be careful about that, right? So here's the thing. This is the upper bound for the whole thing. This is the lower bound for some of it, and this is the lower bound for another part of it. So if you're going to integrate with respect to x, how many integrals do you need?
4.
No, 2. You need 2. Too many. I know. You could do it in 5. I guess you can arbitrarily break things up as much as you want. But you just need 2, because how many times does the lower bound change? It changes once, so you have to break it apart for each case. So if you were going to integrate this with respect to x, you would need an integral that does this region right here. Everybody sees that one right there? And then what happens at that intersection point? It changes to a different lower bound, so then you have a second region right here. If you did it with respect to x, what am I hinting that you should do? Do it with respect to y. Turn your head 90 degrees sideways. How many upper bounds do you see? 1. How many lower bounds do you see? 1. So instead of integrating with respect to x, you integrate with respect to y. So you turn it 90 degrees to the right. That's the standard thing to do. So in this case, what's the upper function? Let me give you colors here to work with here. You see this right here? Is that going to be your upper or your lower function? Upper. That's your upper function. So what are you going to end up with? You have the integral, and the upper function is what, y equals x minus 1, right? But you're doing it in terms of y. So what is it going to be? X is equal to y plus 1. So you have y plus 1, and then you had y squared equals what? 2x plus 6. What do you isolate? You isolate x, and end up with x is equal to y squared minus 6 all over minus y squared minus 6 all over 2. What's the only thing left for us to figure out? No, we need the limits. Oh. This is a definite area. We need a definite integral. So you need the lower y value and the upper y values, right? Because you're doing lower to upper. How do you find those y values? Set them equal to each other. Well, you know that, we have y plus 1. Sorry, y plus 1 is equal to y squared minus 6 over 2. How did I get that? You have these two things, right? Solving for y. So you have 2y plus 2 is equal to y squared minus 6. So what do you end up with? You end up with 0 equals y squared minus 2y minus 8. So 0 is equal to y minus 4 times y. So y is equal to negative 2 and 4. So what are our limits of integration? Exactly. If you're being forced to break an integral up into multiple integrals, ask yourself, is it helpful if I change what I'm integrating with respect to? In this case, you go from needing 2 to needing just 1. And not only that, this integral over here is kind of annoying because you have the positive one, you have the negative one, you have to deal with a radical. It's not that bad, but it's annoying. This right here, this one right here, is just a little bit cleaner. Right here.
Yeah.
Yeah, it's literally just undoing the power rule 3 times. That's it. It's pretty clean. Pretty clean.